so today we're looking at lesson 44. We're going to look at mechanical waves, superposition principle, wave reflections, and speed along a string. So hopefully you'll understand mechanical waves, superposition principle, wave reflections, and speed along a string after this lesson. So light waves are electromagnetic waves, and electromagnetic waves require no physical medium for their propagation. You don't have to have an actual medium for light waves to travel. Therefore, light waves can travel through empty space. That's why light can travel in outer space. Even without any medium, light can still travel. Waves that require a medium in order to propagate are called mechanical waves. So sound waves and waves in strings, springs, and water are all examples of mechanical waves. They have to have a medium in order to travel. So if there is no medium out in outer space, is sound going to be able to travel? No, because sound has to have a medium in order to travel. The properties of these waves can be predicted using Newton's laws of motion. Mechanical waves that move along a string are called transverse waves. The fibers of the string move up and down, yet the energy of the wave moves along the axis of the string. So the fibers of your string are going to go up and down, up and down. So you're going to have it going up and down, up and down. But the energy is going to move along the axis of the spring. Okay? Your string is going to stay here, and it's just going to oscillate up and down, but your string isn't actually going to move. It's going to stay tethered here and here. The energy is going to transfer. Many wave motions have both longitudinal and transverse wave characteristics. A tidal wave caused by an earthquake is primarily a longitudinal pressure wave, but it also has transverse wave properties. So it is both a longitudinal and a transverse wave. Both longitudinal and transverse waves and combinations of those can be described by this relationship, V equals F lambda. We've talked about V, velocity, F is our frequency, and then lambda is our wavelength. Looking at the superposition principle, experiments show that when two or more traveling waves are moving through a medium and the amplitudes of the waves are not too great, they're not too big, the resultant wave can be determined by adding together the displacements of the individual waves point by point. So as long as you don't have waves that have extremely large amplitudes, then add two or more waves together, and that gives you the total displacement at each individual point. We identify the remarkable result by calling it the superposition principle. So looking here, waves A and B are in phase and can be added together. This is an example of constructive interference because as this wave is at a peak, this one's at a peak. As this one's at a low point, this one's at a low point, etc. They are in phase, they're moving along in the same pattern at the same time. And so those are constructive interference waves. These waves are out of phase. As one goes up, this one is up, this wave is down. As this one is down, this wave is up. They're opposites. And so if the amplitudes of the waves are the same, then the sum of these two is that there is actually no wave at all. And this subtracting amplitudes is called destructive interference. The intensity or strength of any wave is directly proportional to the square of the amplitude of the wave. So the intensity of any wave is directly proportional to the square of the amplitude. It's interesting to note that one consequence of the superposition principle is that two or more traveling waves can pass through one another without being altered. We can observe this by dropping two rocks into a pond and watching the waves pass through one another and emerge without change. Or if you've ever been on the river or at the lake and you've got your boat and it's traveling, going this direction, you've surely noticed that you leave a wake behind you as you travel. And if you have another boat that is traveling this direction as it goes through, and it's going this direction, its wake is going to look something like that, and you're going to see both of them. The waves will hit each other, and then they'll just keep going. They don't really change. I don't know if y'all have ever noticed that, but that would be something that you can observe next time you go to a body of water and you see some boats that are moving around. But you can also just take two rocks and drop them and watch the waves as they expand and see how they don't change. Sound waves from two different sources pass through one another as necessary, so that the sound one hears is a combination of the two individual sounds. And this is an example where you drop two rocks into the water, and it shows the waves that are formed whenever you drop them in at the same time. And so we have constructive interference right here at all of these points where they are crossing each other, and then you have destructive interference in the middle. So these points over here are going to be destructive interference. Whenever you have two sources that emit frequencies that are slightly different, an interference occurs that's measured in beats. That's not talking about like rapping beats or anything like that. That's just how that's the word that they use. It's measured in beats. So these are two pictures from the book. We have two waves whose frequencies differ by 2 hertz. This first wave here, you see as it oscillates, in 1 second it had 10 and then 10 cycles, and then the second one, in 1 second it had 12 cycles. On the right, this is what it looks like when you put them together, the resultant wave of combining wave 1 and wave 2. And the beat frequency of these two waves, waves 1 and 2, is 2 hertz. And the number of beats per second always equals the difference in the frequency of the two waves. So wave 2 had a frequency of 12, and wave 1 had a frequency of 10. And so the difference of that is 2, and so that's why we have 2 beats on the resultant wave. 12 minus 2 is 10. Okay? So looking at this example, on a day when the speed of sound was 292 meter per second, two speakers 1 meter apart emitted a signal at a frequency of 682 hertz. I'm going to move this over a little bit. What was the wavelength of the sound waves? So for part A, we're going to use that little formula they gave us. V equals F lambda. Our V is the speed, which they told us was 292. And our frequency is F, and they told us our frequency was 682. And we're looking for lambda, which is our wavelength. And so if you divide that, you're going to get that lambda equals 0.4282, which if you use your significant digits, we have 3 here and we have 3 here. So our final answer is going to be 0.428 meters. So that'd be part A. For part B, a dog was 3 meters from speaker B. How far must he be from speaker A to to detect destructive interference. So for him to have destructive interference, he must be n plus 1/2 length wavelengths closer or further away from speaker A than from speaker B. And so if we wanted him to be further away, then we would just say he is 3 from B, and so we just need to add 0.4282 over 2. And so that would be if we wanted him to be further away, or if we wanted him to be closer, we would do 3 minus 0.4282 divided by 2. So this would work for any one. We could keep changing it. The book is just going to let the n be 0, and so you basically just have to add half of a wavelength. And so our wavelength was this number here, the 0.4282, and so we took half of that, and you can either add or subtract it, and that's how far away you need to be to detect destructive interference. So I'm going to go back real quick. Here, destructive interference, it has to be halfway in between these points. That's where you get the destructive interference. So that's when we had the n plus 1/2 wavelengths. You could set up n to be any integer, but it just said how far does it need to be to detect destructive interference. It didn't say he needed to be a certain distance from A or anything like that. It just asked what could be a possible answer. So if you solve these two numbers, you would get 2.79 meters, and you would get 3.21 meters. Okay, so now we're going to look at wave reflections. Whenever a traveling wave reaches a boundary between two mediums, part or all of the wave is going to be reflected. Sometimes a reflected pulse is in the inverted form of the original pulse. So do y'all see how this one is going up, and then whenever it goes back, it's going down? Sometimes it has the same form as the original pulse. So it can be traveling up both ways. If the end of the string is fixed, as in the ones over here on the left, the pulse is going to be inverted. So as it travels closer and closer to the wall, it's getting closer. Whenever it hits the wall, it's going to rebound and go backwards. Okay? But on the right side, E, F, G, and H, the end of the string is connected to a ring that is allowed to move up and down. And so as it gets closer and closer, the ring actually moves up. And so then whenever it rebounds, the ring falls and our pulse gets pushed back up, and so it just travels back. So that's the difference if you have it connected to a fixed area or to something that can go up and down like a ring. Speed along a string. The speed of a wave along or through a particular medium is determined by the elasticity and other properties of the medium. These properties can include density, the bulk modulus, shear modulus, mass per unit length, and tension. We have found by conducting experiments that the speed of a wave along a taut string is going to depend on the tension, that's T, of the string, and its mass per unit length, which is m sub L, as described by this equation. So the velocity is going to depend on the square root of the tension over the mass per unit length. And we remember that when we discussed the spring constant K, that was with Hooke's law, I believe from lesson 41, and the energy stored in a spring, we considered only perfect strings. These springs were figments of our imagination because they did not have energy losses due to friction of the molecules caused by whenever it's deformed. So whenever it was deformed, we didn't lose any energy. We had ideal springs. They weren't actual real life springs. They were idealistic. The string that we are discussing here is going to be an ideal string, and thus an ideal steel string is going to have the same motion characteristics as an ideal nylon string. Even though in real life that wouldn't be the case, on these they're ideal, and so they'll have the same motion characteristics. So looking at an example, we have a mass of m kilograms. It's used to provide tension for a string as shown. The speed of a pulse traveling along the string is v. By what factor should the mass be increased in order for the pulse to have a speed of 3v? So we're going to start with our formula. V equals T over m sub L. Now, the T, it tells us over here, actually equals the mass times the gravity. So that means that our formula is actually the square root of mg over capital M sub L. Now we want 3v, and that's what they tell us here, 3v. And so we need to multiply the right side by 3 as well. That should be a capital M. Okay. And so now we want it to change the M. So we want this 3 to actually be on the inside of the radical. Well, to move it to the inside of the radical, we're just going to make this the square root of 9mg over capital M sub L, because the square root of 9 and 3 are the same thing. So in order to increase the speed by 3, by a factor of 3, then the mass must be increased by a factor of 9. So that would be your answer there. So you may not have really needed to show all that work now that you kind of understand what they were asking for, but that's what you would do there. Okay? Looking at one more example, we have a string with a uniform mass of 0.4 kilograms and a length of 5 meters. The tension is provided by a 3 kilogram mass as shown. We want to find the speed of a pulse on this string. So we're going to use our formula. And to find our T equals mg. And so T is 3 times 9.81. Our M sub L is the mass per unit length. I'm going to go back to that page that had the formula for you. It says it right here, mass per unit length. That means the mass per means divide by, and then the length. Okay, so mass divided by length. So our mass here, the string's mass is this, 0.4. So we have 0.4. And then our length is 5. And so if you divide that, you would get 0.08. So now we're going to plug our tension. When you multiply 3 times 9.81, you get 29.43 over 0.08. And if you plug that into your calculator, you should get 19.2 meters per second. It's velocity, so those are your units, meters per second. Okay, so your homework is numbers 1 through 20, and then I want you to make sure to look at the curveball questions. They may show up somewhere on your test for bonus at some point. I'm not really sure. We'll just have to see. But then make sure you do all of those so that you can go over any questions you have tomorrow.